Start this all over again. All right, so for this warm-up, h of x is defined as to be equal to f of x times g of x, and they're asking us to find the derivative of h of x evaluated at 1. Okay, all right, so our volunteer was kind enough to work out this problem and saw that if you're going to take the derivative of something that has a product of two functions, you need to apply the product rule. Now, if you're going to write out the product rule, though, the one thing that I might add is don't plug in the 1 just yet, right? If you're still going to be using x's, use the x first, and then once you plug in the 1, then you can go ahead and actually put the 1 in here for x. But that's not a big deal. It's just notation. You still get the same credit. You still get the work. It's just a little bit like a very minuscule thing. And I think most graders won't care that much. All right. So now that we have f prime of x times g of x plus g prime of x times f of x, derivative of the first function times the second function, plus the derivative of the second function times the first function, all we have to do now is plug in the values that are in the table. And I'm going to assume that those are right. We have a 10 here, -5 there, -7, and a -6. That's exactly it. So 10 times 5 is -50, plus -7 times -6, which is going to be +42, and you get an answer of -8. That's beautiful right there. Beautiful. And that was done by Monica. That's done by Monica. Thank you, thank you. All right, let's take a look at Juliet. All right, same thing. Let me go ahead and add a sticky so I can give you credit for doing this one today. Do I hit save? Yes, I do. And I just move this over here so I know that you did this. All right, and Juliet, did you write this by hand? Oh, was this done with your mouse? This is impressive. But same thing, look. She wrote down that we're looking for h prime of 1, and she wrote down the product rule and wrote down 1s inside for all these x's, right? And that's beautiful. Same thing, right? We just evaluated looking at the table. Once you know which rule to apply, and in this case, once you applied the product rule, we just go ahead and do that and plug those in. And she also got a nice -8. I have so much fun with this. Look at this laser. All right, anyways, awesome job, guys. Awesome jobs. Thank you. Thank you for sharing that out with us and how you attempted this problem. And that was beautifully done. Okay, so with that being said, we're pretty much done with chapter 2, right? You guys know what that means, right? We just move on to chapter 3, right? But before that, what's that favorite thing that you guys love to do once you finish the chapter? Pizza party. I mean, of course, you could always have yourself a pizza party, right? Everyone get your own pizza. We'll do it virtually. But no, that's not what's going to happen after you finish chapter 2. That's right, a test. Oh, Monica, you pressed the wrong key there. I think you meant to hit the other parentheses. It's the other way. You know, I think it's supposed to go this way. That way. It's not that bad. All right. So yeah, we have a test coming up. All right, we have a test coming up. So I'm going to have a review guide for you today, and plus a Delta Math review for you today that you guys can work on. And we'll do the review. We'll do a couple review problems if we have time today together. That way we can, get you started on there and get the ball rolling. But before we do that, I do have an activity for you guys today that I wanted to do with you guys. And I'm going to need you guys to click on this link for me. It's on my Canvas page, but I'm also going to just give you the link right now. It is going to be a Desmos activity, right? It's a Desmos activity. So we're going to work on this together. So here is what it looks like for me. And let me give you the link right now into the chat. And when you get on this chat, I will see you guys. You need to log in with your school email into Desmos in order for this to work. So make sure that you're logged in with your school email on your browser. And then when you go into Desmos and it asks you to sign in with your school email. Oh, that's actually a good question, Leslie. I'm sorry, I should have told you. Since we're starting the review today, I think it'll only be fair to take the test within a week from today. So I'd say next week on Thursday would be fair. I don't think we would do next week Tuesday because that's just ridiculous. I don't think we'd have time to review only on Monday and then take the test on Tuesday. I think we should take a mini practice quiz on Monday, review on Tuesday, and then your test will be on Thursday. Okay? Your test will be on Thursday next week. Okay. So yeah, looking good, guys. If you see your names on here, that means you were able to join correctly. Huh. Jeffrey, how'd you get only your first name to show up and not your whole name? Either way, I know it's you, right? There's no other Jeffreys in this class, right? There's only one Jeffrey. Yeah. Okay. So yeah, go ahead, guys. Click on the link. This is the Desmos activity I need you guys to take a look at. Desmos link. This also will get you to join my Desmos class. So I will be assigning, if so, I will be assigning stuff on there as well. Okay. So Jeffrey is in there. Fatima, Grace. How are you guys getting only your first names instead of your whole names? Are you guys joining with only well, you're joining with your CVU account? That's interesting. How do you only get your first name to show up? That's kind of neat. All right. So, whoops, did not mean to click. It asks you what name you want. Oh, I thought it just did it automatically. That's cool too that it asks you the name, but I thought it was just automatic. You just click in and it'll just give it to you. All right. So this is the first slide, and I have you restricted to this one, and I want you guys to answer for me, right? So the derivative, remember, of course, the derivative is just the slope of the tangent line to a function, right? So they give you a nice thing here that you can move along, and this green dot is just a random point on the function that's drawn there. The purple line is the tangent line, right? The line that's tangent to that point. So we have it here, and you can actually draw it along. You can see how that tangent line works. It's tangent line over here has a positive slope, then it has a negative slope, and then it goes back to a positive slope. So here's what I need you to do for me. Where on this graph do you see the slope to be equal to 0? Drag the blue dots to the x values that you think the derivative will be 0. So there's blue dots right here. You can't move it up or down. You just move it left or right. And move it where you think the derivative, slope of the tangent line, is equal to 0, right? Wherever you want it. There's 3 dots, but that doesn't necessarily mean that there's 3 places, so they just give you an extra one just in case. But move it to where you think the derivative is. Okay? All right. Once you feel comfortable with that, I am opening up the slides now, so you can move along to up to slide 4. If at any point you feel like I'm going too slow, you can go past this and go faster than I do. I will be unrestricting the slides as we go along, slowly but surely. So make sure you type in an answer here. I do want to see what your answers are. I'm going to go ahead and click on anonymize this so that we can't see who's typed in what. By the way, there are 33 students in this class, but I only have 28 of you who are on this Desmos activity. I am missing a couple of you guys. Are you guys not able to click in because the link doesn't work, or you're having trouble creating your account? Who is not in here? Who is not in here? I don't really want to go through the list and look, but I lost my green dot. Oh no, did you slide it off the chart? It went too high up. Same. Oof. All right, listen, all right. I'm going through the double check. Who is not in right now? Looks like we're missing Alejandra. Andrea. No, Angela's right there. Aurelia's right there. Do we press share with the class? Yes. Once you typed in your answer, you click share with the class, and they will be submitted for that. Angela's right there. Aurelia's right there. Brandon's right. Wait, I don't see Brandon. Brandon, where are you at? Oh, there you are. There's Brandon. I'm blind. Brian, Haley, Calvin, Cheyenne, David, Diana, Emily, Eric, Ava, Fatima, Frankie, Gracie, Ilias. Where are you, Ilias? Oh, there you are. Right when I'm about to call your name, you clicked in. Ilias. Jackie? You in there, Jackie? Not yet. Hopefully you can work your way into the link. We got Jeffrey, Jocelyn, Joe, Juliet, Julia, Kimberly, Leslie, Max, Monica, Sam, Rahish, Shirley. All right, so I'm missing Sydney, Jackie, Alejandra, and Andrea. Are you guys there? Are you guys able to get in? I'll put the link one more time if you guys are not there yet or you came a little bit late. Okay, so once you move the blue dots, right, last part is I want you to write down when do you think the derivative will be positive and when do you think the derivative will be negative? And just type that out and share. Once you hit share with the class, you can go ahead and hit the next slide. I see some of you guys are still here doing it. Hit the next slide and you can verify your answer once you share with the class. Okay, once you share with the class, you can go over there. So I want to take a look at some responses here. Oops, let's anonymize that and not just have it. At x equals to 1, right? At x equals to 1, Alan Turning is saying that it is positive when x is equal to 1 and negative when x is equal to 3.5. Now remember, we're not asking where the function is positive and where the function is negative. We're asking where the derivative is positive and where the derivative is negative. Okay? It'll be negative between the blue dots and positive after each of the blue dots. I like that answer. I like that answer. Right? Because we're looking at the tangent line, right? The slope of that purple line as you move that green dot around. By the way, if I move it here, does it move it for your screen? I wonder. No? Oh, yes? Joe, is that you? Never mind. Let me see. Let me just go in here and just start messing with people. Oh, here's the one whose dot is too far. How did you do that? Can you zoom in and zoom out? You can't even move the graph. Someone's dot is off the charts. The derivative is positive after the two dots and negative between the two dots. That's beautifully answered. I like that answer, right? And you can see that by looking just at that purple line. All right, let's take a look at a couple more of these. The derivative will be positive. Oh, you're still typing it out there. I think the derivative will be positive from -4 to -1. Yeah, I can see that, because that's where it becomes 0. And from 3 to 6, okay, 0 to from 3 to 6, it looks good, right? And it'll be negative from -1 to 3, right? In between there, you can see it has a slope that is going down. Okay, very good. Again, once you typed in this answer, go ahead and move on. And once you pass the second slide, you can go on to the third slide and see and answer the same question, but for the third slide, right? So you're going to verify your prediction on slide 2. I'm still going to be looking at the answers on slide 1, all right? But if you guys are done looking at it and seeing your fellow classmates' explanations, you can move on to the next one. But yeah, let's see here. I'm going to snapshot that one because that one's beautifully written. It has intervals where they are. It has the numerical values there. The slope will be 0 at x equals 3 and x equals -1. The slope will be negative between that, and after that, the dots will be positive. I like that as well. Okay. These are great answers, by the way. Positive if the function goes negative. Be careful with that saying, because the function is negative down here, and it's negative over here, but their derivatives are positive there, right? The slopes of those tangent lines are positive, even though the function itself is negative. And that's the part that you need to keep in mind, right? The derivative isn't necessarily looking at the function value. It's looking at the value of its tangent, the slope of its tangent line, right? How did you guys get that thing to go off the... Oh, and then if you let go, you're not going to get it back. I see how you did that now. Ooh, that's actually impressive. Okay. So looks like you have positive slopes here, negative slopes here, positive slopes there, right? We got the snapshots there. I wonder what snapshots do. If I drag it and drag that one. Oh, I got to play with this later. I don't know what this does. Add photos from another device. Open this dashboard here. Huh. Interesting. All right, so let's go over to slide 2. Let's go over to slide 2. Verify your prediction. They make it so that it actually graphs the derivatives for you at each of these individual points. So you can slide this along here and you can see what does the derivative value actually have at these specific points at these specific points. So check this out. As I scroll this along, the purple dot is moving along here. So what you need to imagine is if you're moving your dot from earlier, right, and you're able to see the tangent line, you can see the slope of it. And as you can see, it's higher over here because it's very steeper. It's steeper over here until it approaches this part right here where you say the derivative is equal to 0, right? You can actually see that tangent line is horizontal right there. So what happens on the graph? Bam! Once the derivative reaches this point right here, you have a derivative of 0. You have a tangent line that's equal to 0 there. Where else does it happen? Right here. But before that happens, your derivative travels down into the negative parts. That's because the slope of the tangent line is negative. And that's what the graph of the derivative represents. It represents those negative values for the negative slopes of those tangents that are between -1 and +3. So the derivative is down here in the negative values because the tangent lines you saw earlier were negative, right? We're going to go ahead and scroll it all the way through. And it just starts going up, and it just goes up faster and faster because it gets steeper and steeper as it goes off towards the right over there. So there's your derivative. It looks like that. Okay. I think that's kind of neat. You can watch it actually like oh. And see it go back and forth. All right, by the way, there's nothing else you can do on this one. You just slide it, just take a look at it, and then move on to the next slide, guys. Move on to the next slide, onto slide 3. Who's still on slide 1? Who's still answering on slide 1? There's oh, it actually shows the name if I hover over it. Let's not do that. If you guys are still on slide 1, answer the questions as best you can and move on to the next one. I'm still missing quite a few of you guys in here. I have 34 students, but only have 29 who are in this activity. So I don't know where the rest of you guys are. But if you guys could, at least join in there and follow along with us. We're going to go ahead and go over to slide 3. And I have it right here. What is happening in the red graph of f of x when the purple derivative graph is 0? And how does the derivative change when f of x is increasing versus decreasing? And I kind of talked about that. I shouldn't have talked about it too much, but I kind of gave it away. And you can kind of see what it's doing here because remember, the purple dots, right? Those represent the values of the slope of the tangent line, or in other words, the derivative, right? So you're looking at the original function in red here, and you're looking at its tangent lines and just moving it along, okay? So type in your answer for that one, and then whatever you say it is, I'm going to take a look at some of your answers here. The red graph is at its zenith or peak when the purple graph hits 0. That is beautifully answered, whoever put that there, and you are still typing out some more. Whoever is Kurt, that is a beautiful answer. I like that. The red graph is at its peak when the purple graph hits 0. That's beautifully worded, right? Okay. When the derivative graph is 0, the original graph is hitting its maximum y value, right? Good, good, good. I like that. So that's this point, right? I think you're referencing this point right here, but it's also hitting its minimum value over here, isn't it? Now, we don't call that its max or its min. We actually have a special name for that because these points over here are of greater value. So this would actually could be your max over here. But what we call for this one, it does use the word max, but we call this thing a local max, meaning it's a max of everything around it, right? So it's a local maximum. That's the new term, new vocabulary for you. This is a local max right here. And this right here is considered a local minimum, right? By the way, these are beautiful answers that you guys are typing out. I'm going to go ahead and save this one. Save this automatically, but I'm going to go ahead and save this and go through all of these guys. When the derivative is 0, the red graph reaches its maximum and minimum values. The derivative changes when f of x is increasing. I'll leave you to finish that one. That's pretty cool, though. I can see you typing it before you even submit it because you're still typing it out. That's awesome. Once you finish this, answering this, and you don't want to wait, you can just go ahead and move on to slide number 3. I'm sorry, we are on slide number 3. So go ahead and move on to slide number 4 and try to predict the next function. Try to predict the next function. See what you get there. Okay, let's see here. What else we got? The red graph is at its local max and local min. Ah, you're using my terminology. I like it. When the derivative is 0. Can you drop the link? Of course, Oscar. Of course. Yeah, get in there. Again, I have 35 students now. I'm assuming, Oscar, you just joined. So click on that link, and you can work at your own pace. I have it open only to 4 slides, so try to catch up to us. We're only on slide 3 right now. But there's still a good handful of you guys who aren't participating, and I don't know why. Maybe you guys are busy with something else. But I think I'm still missing Alejandra and Andrea. Let me go double check before I actually make that claim. Sort by name, take off an animate. Yeah, I'm still missing Alejandra and Andrea. Are you guys having trouble getting in there? You're here? You're just not able to get into that link? It just doesn't work for you? Is it laggy for you? Is Desmos not working okay for you? Just double checking if it works or if it doesn't work. No, I'm trying it again right now. Okay. Let me know if it doesn't work though. That's the only thing. Just let me know if it doesn't work for you guys, and then you can just follow along with me on the screen. I just need to know why it doesn't work, so we can try to fix that, or I can talk to, because this has happened in my other class. They weren't able to get in sometimes, so we had to have them do it on a different device. Okay, I'm at 30 students now out of 35, so I'm missing 5 of you still. So get in there when you guys can. Get in there when you guys can. So then go back to, actually, let's see here. Fatima, you're still on that first one? Oh, did you go back to the first one? Because I have answers recorded for you for the other 2. So did you go back to that one? Ilias, did you just like fly all the way to the 4th one? You didn't want to type out an answer on that first one? Oscar, you just joined. Sam, you still on that first one? You should be done with that one, hopefully, and type in your answer for that one, and move on to the 3rd one where everybody's answering right here. Oops. All right. So the derivative is at 0 when the red graph reaches its peak. That's a good word right there. Its peak right here, but it also reaches a bottom peak, right? A lower peak, right? What would you call that? Maybe you're going to use the word peak. What happens is that the purple crosses at 0 when red slope is at 0. That's exactly it, right? When the slope of what, though? Make sure you say it's the slope of the tangent line. Okay, the slope of the tangent line is at 0 here and here, right? When the derivative is 0, red is at its highest. Yeah, be careful with that, though, okay? It's also it's higher over here than it is right here, right? Same thing as this one right here. This is, you got the right idea. There's something special happening when the derivative is 0. It does reach it when it's at its highest, but it also reaches when it's at its lowest. But again, you can use this phrase if you're going to say that it's at its local highest and its local lowest. It's local max and its local min. Okay? That's those guys right there. The derivative hits the local maximum and the local minimum. That's exactly right. That's exactly right. That's good. F of x is increasing when the derivative stays the same. When f of x is decreasing, okay, you're still typing it out, right? So we see this special part, right? The derivative equals to 0 when you have a local max and a local min. But take a look at this, guys. When the derivative is positive, do you see the red line here? The red line is increasing. You see that? When the derivative is positive, that's all these purple dots right here. The red line looks like it's increasing, right? And when same thing over here, you see right here, this is where it's 0, and then the purple dots go up over here. Right here, this red line, right, is increasing all the way as long as your derivative is positive. You see that? Whenever your derivative is positive, whenever your purple dots right here are above the x-axis, the red lines looks like they're going up from left to right. And it doesn't matter where you're looking at this. You could be looking at it over here when the function is negative. Even though the function is negative, I don't care about that part. I just care about the fact that it's increasing. Do you see that? This red line is going up when my purple dots are positive. You see my purple dots are positive? That makes my red lines go up. And same thing over here, when my purple dots are positive over here, my red line is going up from left to right. But look at where my purple dots are negative. It's between these two specific values, -1 and 3. And in between those those values here, my red function is going down. It's a positive value here. The red function, the original function, it is a positive value between there. But it is decreasing as it's going towards here because its derivative, right, is negative, right? Since the derivative is negative, that means the slope of your tangent line is going down, which kind of makes sense that you can see like, hey, your function is going down between those two. It's going down between those two. Okay. Once you get that answer in there and shared, go ahead and head over to the 4th slide and let's see your predictions for this one. Same thing, but it's a little different this time. The function is a little bit different. Can you guess where the slope of the tangent line is 0? Wherever you think that is, move the blue dots to where you think that would be. Where do you think that would be? Right? And again, I don't think you use all 3 dots in this case. You're probably going to use only 2. And move it to where you think that will be. When do you think the derivative will be positive? And when do you think the derivative will be negative? And what do you think the end behavior derivative will be like? So I'm going to give you guys a second. I want you guys to write out your answers for this one. And where do you think the derivative will be 0? Right? Where is the tangent line, the slope of the tangent line equal to 0? Move the blue dots there. And where do you think the derivative will be positive, and where do you think the derivatives will be negative? And this 3rd question here, what do you think the end behavior is? What do you think the end behavior is? Oh, nice. You guys found the infinity insert when you guys are typing? Yeah, you have little icons here. There's a math type here. You could type out all the different math functions if you want. There's like square root function, there's percentages, functions itself. Actually, how'd you find the infinity button? Where is that? That's a pi logo. Yeah, that's interesting. Wait, where'd you find infinity at? I should know, but I don't. That is actually interesting. Yeah, one of you guys have the little infinity sign in there. The world may never know. Is that you? It is you, Brian. Clever, clever. Oh, you found it as well, Kurt. Whoever Kurt is. Oh man, this is beautiful typing. You are using this notation right here for you're using interval notation, and that is just beautiful. Whoever is Alicia, I'm gonna. Gracie, it's you. That's beautiful, by the way. That's beautiful. The derivative will be posted between 2 points. Positive. Sorry. The derivative will be positive between 2 points. My eyes are playing tricks on me there. So -1 to 1. And the derivative will be negative from -infinity to -1 and 1 to infinity. And I like that. You can kind of see the I hope you guys are able to see why some of these answers are being typed the way they are. Right, and if you're looking at my screen, you can see what those answers are. And you know what? That's just, that's so good. I haven't snapshot that, but look, right? All they're looking at, right, is the tangent line. The only difference is this function doesn't have a little dot for you to slide around to see it, but you can kind of imagine it, right? If I move this dot here all the way up to -1, all those tangent lines look like they're going to be negative. They look like they're going down. And then in between here, the tangent line turns into a positive. And then right here at 1, it goes back to being negative. I'm going to go ahead and open up the next couple slides there so you can go ahead and verify your answer if you already submitted your answer for slide 4. You can go to slide 5 now and take a look and see what does that derivative actually look like. Okay? And then once you see what that derivative looks like, you can go to slide 6 and summarize what you saw going on there. Okay? You can summarize what you saw going on there. All right. I'm going to go back to these answers here, though. Let's see here. Huh. The word you're typing out is coming out super fancy, whoever it is, Alan Turing. Derivative will be... Are you typing with the keyboard, the digital keyboard that's on here? Is that why you got it to look so fancy like that? Derivative will be, let me go over here. I'm gonna try that. Are you typing with these guys? You are typing with this. Who's doing that? That is actually, you're going to be there for a little bit if you're going to type out a whole sentence. What we got here? The slope of the tangent line will be 0 at x equals 1 and x equals -1. The derivative will be positive between -1 and 1 and negative from infinity to 1 and from 1 to infinity. That is also the same. That is beautiful. Good answers, guys. Very good answers. Good observations that you guys have going on here. And way to go. But we'll never find out, though, how people like Brian and whoever is by heart, oh, Brian again, is typing in those infinity signs. We'll never know, will we? We'll never know. I tried to figure it out. I couldn't do it. You just type infinity? Oh, you just type infinity. What? Copy and paste from Google. Oh, wait. Look. You just have to hit this this type math, and you can type out math in infinity. And it puts up infinity. This is amazing. Can you type out square root too? Square root. Oh my goodness. Oh my goodness. That is awesome. That is awesome. Oh, were you guys doing it differently? You were just copying from Google, copy and paste from Google. Oh, okay. I thought you guys figured that out. I was like, man, you just type out stuff. I was just lost the whole time. Oh no, Juliet. Do you need help catching up? Or are you okay with going through the slides and following the directions on there? Do you need help with any of it? Where are you right now? Hopefully you're able to catch up. You're good? Okay, you're good. All right, you're good. Let's go ahead and move on and verify your answer. Take a look at this function. Take a look at this function. Let's play it out. So you guys are right. In between -1 and 1, right? In between -1 and 1, you can see it. The derivative is positive there. The slope of the tangent line from -1 to 1 is positive. Those purple dots are all above the x-axis, aren't they? And then once you get past that, all the purple dots are negative, right? But check out how they're trending. Check out how they're trending. What's something interesting you guys see about those purple dots? They're all negative, aren't they? They're all negative slopes. But there's something else that's kind of interesting about those negative slopes, isn't there? Isn't there? Oh, can I zoom out? Yeah, if you keep looking at this, right? It's not reaching 0 again. It's not going to give you another derivative or another tangent line that's 0. But it looks like it's doing what? It's getting closer and closer, right? So if you guys could go on to slide 6, type out your summary. How was your prediction? What did you confirm, and what were you surprised by? And I'm looking at your answers from your predictions. I think a lot of you guys were actually really good on these answers, right? Really good on these answers. So your predictions were pretty good. And what did you confirm? What did you realize actually is happening there, and what were you surprised by? Okay. Once you get this answer down, I'm going to go ahead and open up the slides for the next 3. The next predict, actually, no, just the predict. Just the predict. Right? I actually don't know how to go backwards on that. Well, that's up to you now. So go ahead and do the next prediction, and then go ahead and move on to the verify once you've done your prediction for the next slide. So yeah, type in how good were your predictions, right? What did you confirm, and what were you surprised by? Okay. All right. While you do that, I need to open up something real quick. Give me 1 second. Open up over here. Bro. No. No. Move over here. There you go. There you go. I'll close you over there. Good. And I think that's what I need to open. I'm going to open you up over here while you guys are working on the next slide. So the next one, I want you guys, once you typed in your summary, next one, when you're ready, try to type out your prediction for this one. Try to type out your prediction for this one. Okay. Do, 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 do. All right, let's see here. How many of these do I want? I want you to do like 2 of those. 2 of those. All right. Once you verified, by the way, go ahead and move on to the reflect. Okay, once you verified, go ahead and move on to the reflect. And then we'll wrap this up and see how you guys are doing at the end. I'm trying to set up your Delta Math review here for a second, so if I go quiet, don't mind me. I'm just checking. Oh, that's going to be fun. There's that. All right, let's take a look at some of your answers here. How are we doing on here? I think the graph of the derivative would be negative at these corners, question mark. Okay. On both sides of the corners, just one of the corners, or only approaching the corner from a specific side? Right, that's a good thing to point out. I think the graph of the derivative just won't have a point where the corners are. Ah, okay, I like that. The slope of the tangent line is 0 at x equals to -4, -2, and 0. So, okay. Okay. At the graph's corners, I think the graph will not be differentiable. Oh, now here's the thing. Those 2 sentences right there contradict each other at specific points, specifically the corners, right? If you think the corners are not differentiable, which you are right, by the way, corners are not differentiable. That means that the tangent line, the slope of the tangent line at that corner can't actually equal to a number, right? It actually would be undefined. So we can't say that it's equal to 0 at x equals to -4 and x equals to 0. So be careful with that. The slope of the tangent line does equal to 0 at certain points, but if you're going to tell me that the corner is not differentiable, then we can't say that it has a slope of 0 at the corners as well. That's where it contradicts. If you have a corner and it's not differentiable, that means the derivative value will not exist at that point, right? Good answers here. Let's take a look here. The slope of the tangent line will be 0 at -2. That's good. Since there are corners, they don't have any local linearity. Local linearity. That is a beautiful use of the vocabulary. And local linearity is an important concept that you need to make sure you understand. Because at those points, there's no derivative there. There's no derivative there. So take in your answers there. And if you could, follow along with me into this part, and you can take a look at the graph of this guy. All right, take a look at the graph of this. All right, so when I graph this function, oh, it's derivative. Take a look here. These are all negative negative slope values, right? The tangent line as I'm coming across up to this corner from the left-hand side are all negative, right? They're all negative up until here, where it just disappears and then jumps over to there. And that's because since there's no local linearity, the derivative never approaches the same value from the left-hand side as it does from the right-hand side, right? The derivative does not approach the same numbers. And if you zoom in, you actually see this happening, right? The derivative on the left-hand side goes more and more steep since it's a corner. And the derivative on the right-hand side goes more and more steep this way. It makes it more steep towards the positive value, whereas the left side makes it more steep from the negative value. So they don't approach the same number from the left hand and the right hand. And remember, that's all the derivative is. We're taking the limit as it approaches that point from the left hand and the right hand. And since the limit does not exist, the derivative does not exist at that point. And that's awesome, right? That's like, I don't know. I think that's a neat thing to look at. It's just the fact that like you can actually see that. Because when you take derivatives anywhere else, especially at -2, if you take the derivative at -2, right, you actually have a point here and it does exist. But that's because if you look at -2 and you zoom in and you come in from the left-hand side and you come in from the right-hand side, those derivatives both approach 0 at -2. That's why the derivative there is equal to -2. The slopes of those tangent lines approach that same number from the left-hand side and from the right-hand side. And I hope you guys are starting to see. You guys are starting to see all this stuff connects, right? Why did I teach you limits for a whole chapter? That's because that's what a derivative is. It's your tangent line as it approaches from one side, as your secant lines approach from left side to right side to one singular point, right? One singular point. And that's your tangent line, right? That's your tangent line. And you're just calculating the slope of that said tangent line. And again, if you come over here to this cusp over here, this pointy part over here, right? There we go. It goes up there, right? It goes negative slope, negative slope, negative slope, and then it goes to very, very negative slopes as it approaches this pointy part or this cusp, right? Or this, is that a corner or is that a cusp? Would you guys call that a corner or would you call that a cusp? That looks like a corner. I don't really see a curve into it, but you wouldn't get marked wrong if you call it a cusp or a corner in this particular case. But anyways, right, it goes off towards negative infinity as it approaches this 0 point from the left side, and then it goes from positive infinity to these values right here as I'm looking at it when it approaches on the right side, right? As I approach on the right side. So can you guys go in there and reflect off that? Reflect off these points and see what makes the derivative behave, what makes the derivative's behavior at x equals -2 so different from x equals to -4 and x equals to 0. Okay? All right. Once you get that answered, you can go ahead and move on. I'm going to take a look at some of these answers, but before I take a look at some of these answers, I just wanted to share what the next slides are before I go on. So on this slide here, right, they're going to tell you like what's going to be happening on the next couple slides, right? And this is just something I want you guys to try before you close out of this thing, which is to match the red function with its green derivative. So the red function will be here, the green function will be its derivative, right? So there's a bunch of functions here that you can just move around, and that's what I want you to see, by the way. If you think one is the derivative of the other, so let me do a hard one for you here. Let me give you this function right here, this linear function. The slope of this tangent line is 0, and I see the green line that has that value. You see that green line is at 0. If I believe this one matches with it, all you have to do is drag it on top of it, and then it stacks them together. You see that? Stacks them together. And that's all I need to do. And once that's done, you just click the little arrow and collapse them, and you can go ahead and move on to the next one. But you can also have it open just so you can see like, oh, that's the derivative of that one. What's the derivative of this guy? What's the derivative of this guy? It looks like it has a 0 value right here, and that's going to be this one over here. And I just drag it on top of that one. And again, collapse them when they're done. That way they don't take up as much space, and you just keep going through them. Okay? So answer your reflection question that's right here. Move on to this one and match these graphs up. And then that's going to be it for this Desmos activity. After that, there are 4 more slides. And this one is not something we're going to do together. This is something I'm going to ask you guys to do on your own time if you want. It's more practice, and it'll be asking you to graph the derivative by hand, looking at the main functions that you have there, the red functions that you have on there. So you're going to be graphing them by hand and seeing what do you think the derivatives should look like, and then they'll have the answer at the end for you. So if you guys want to do that, you guys can. All right, so give me a second here. Okay, and that's that. So I'm going to open this all up. You guys can complete this whenever you guys want. But I'm going to go ahead and leave this assignment open. Whenever you guys complete it, I will know, and I can go in there and check off who did what and give you guys the credit for that. All right, so that's that. That's the Desmos activity. Next thing up is going to be your other stuff here. So first of all, by the way, there is another homework assignment. I forgot to add this onto here. So I'm going to put this over here. Let me see here. Let me put this. It's the 2.6 homework, but it doesn't actually have tables. It's just more practice with derivatives and looking at the graphs. You know what? Let's just put that at the end of this one because practicing with the graphs is what we did today. So we did the Desmos graph activity right here. Axis was right there. Oh my, knock me. What are you doing? We'll put the homework right here for 2.6 homework. And then here are the test reviews. Right? Test review for grade, test grade curve. Right? So this is the first one. And this first one is going to be the Unit 2 review, which is right there. And the other one is going to be on delta math. And I'll put you guys know how to get there. The delta math is just the site. I'll post that up today. Right? So let's go ahead and I'm going to go over a couple of review problems with you guys. So if you guys want it's posted right here. I'll put it into the link right now. So the homework is on here. This is the last homework assignment. That's going to be for credit. Your unit review is not for credit. Remember that, right? You don't get credit for finishing this review, but you do instead get a nice boost to your test score if you do this on there. Okay? So that should be your incentive if you want it to be. If you don't want to do it, you don't have to. This is not a graded assignment. It's simply just there for your curve on the test. I really suggest you do that. Same thing with your delta math. Your delta math is not going to be for a graded assignment. It will be for your curve. And if you guys want to know how I calculate your curves, it's based off of if you do both or if you only do one or the other. If you only do one of the two assignments, your curve is going to be based off of a flat, like instead of it being out of 100 points, it'll be out of 95. So it could be as low as 5 points. It could be as high as 10 points on there, right? And which isn't a great curve, but it's still like half a grade. So that's not too bad. Like 5 points is not too bad. That's doing one of them. But if you do both of them, and that's the one I really recommend, you get the most bang for your buck if you do both of them. If you do both of them, I enter a more complicated equation for your curve, and it definitely helps those who don't score very well on the test. It definitely does bend that way. If you score like a 99, doing both of these probably won't help you as much, but it still will curve you a bit to get you into that if you really care for that perfect score. But let's say you take my test and you like get a 50% on it, right? One time my how do I explain this? One time my calculations for the curve was super high to the point where all I did was take the square root of the percentage that they got, right? If they completed both of them, the highest curve I gave one time was to take the square root of their percentage. And if you are not familiar with that, here's what that looks like. Percentage as a decimal, right? So if you get like a, that's 100%, that's just 1. And if I take the square root of that, that's just still 1. So that nothing changed to that person who got that perfect. But if someone got a 50% on this test, right? If I curved it with this idea of taking the square root of it, the square root of 0.5 is 70%. So this person who got a 50% they were able to do both the assignments here and earn this curve. So instead of getting a 50%, they ended up getting a 70%. And it works along the way if you get a very low score, and it works along the way if you get a very high score. For example, if you take the square root of a B, right? Let's go with the square root of 80%, someone who got a B on the test, they still get a boost. They still get a boost. It's not as high as the other one, but they still get a boost up to 89%, right? And again, if you try this out, you can see how this works out. But I don't know if I'm going to give you the square root function just yet as your curve. The curve I gave on the last test was I gave, I think, a percentage of what percent you were missing. So if a person got a 70% out of 100, I would do 100 minus 70%, right? And then I do a percentage of that. I would do a percentage of that. And I think for this one, I did 25% of that. And what I did then was got this, and I would take that number and then add that to their original percentage. Now, if this is all sounding too much for you, it is a lot of equations, and I love doing these equations. That's why I do these curves. It's not because I'm trying to help you guys out. I'm trying to do this. No, I'm just kidding. This is actually to help you guys out, but I do them, and they are a little bit more complicated. But the idea, the general idea, is just do both of these assignments, right? Get the better curve, right? If you aren't feeling comfortable with these derivative things yet, I don't want you to stress out about it. We're going to be practicing out the whole year with these derivatives, and if you don't get it now, we're going to keep going until you do get it. And just because you don't get it on the test, then do these assignments right here. Do the Unit 2 review and then do the Delta Math review, and I will curve the crap out of your score, right? If you care so much about your grades. But if you, and then we'll take more time to learn it, okay? We'll take more time to learn it. That's all I'm trying to say here. Get yourself used to doing these assignments before that. The Delta Math isn't up and ready yet. I still need to click and add the assignments, so that should be up by 1 o'clock today. But before that, you can actually start on the Unit 2 review, which, did I give you the link yet? Or did I was too busy going off on a rambling rant. So let me go ahead and give you that link. So here it is, the Unit 2 review. I'll put that into the chat. It's also on Canvas already, so you don't need to memorize or bookmark this. I'm going to go ahead and open up my Delta Math, and I'm going to go ahead and open up a new page for your Unit 2 review. And we're going to take a look at a couple problems together. So that way, look, I'm doing a couple of these problems for you already. So you guys should, you know, thank me. Or not. Right? It's up to you. Whatever you say, whatever you think. Let's take a look at this practice exam. Wait, which practice did I give you guys, by the way? I need to double check that. Oops. Which practice exam? I have a couple practice exams for this one, so let me double check before I start willy-nilly handing out this thing here. So we go here, and there are 14 problems, and I look over here, and there are 14 problems there. Okay, so this is the right one. Okay, so there's 14 problems on this review. Not a lot, guys. Not a lot. You know, take advantage of this. It's a good deal. By the way, for this problem, if you don't write this down, remember all these notes that I do on OneNote are posted online, so you can go back and look at whatever notes you missed, if at any point. And you can also look at any video recordings that you might have missed because, you know, a lot of you guys are going through some stuff, right? So first things first, so this is the very first recent thing that we just learned, which was how to calculate the derivative, right, given a graph, right? How does its derivative look? That's, by the way, that's what this is right here. The dy dx is just a fancy way of writing out derivative, right? Derivative. There we go. So if I'm looking at this function, you should be able to graph what does the derivative look like. And remember, the derivative is the slope of the tangent line. So right here, from here to here, I see that the slope of the tangent line is going to be equal to 0. So guess what? From here to here, my line is going to be right there. See that? Now, from here to here, right, the slope looks like it's a positive slope, and it's constant. It's going up 1 over 1, up 1 over 1, up 1 over 1, up 1 over 1, which means that it has a slope from here to here of 1. Has a slope of 1. You see that? And I need you guys to figure out, should this be, by the way, an open circle or a closed circle? Same thing with that blue line right there. Should that be an open circle or a closed circle? You guys need to figure that out. Now I'm only going to do that halfway. You guys can figure out the last part of it, right? That is a negative slope, so it's probably going to be somewhere down here, and it's also a line as well because it's a constant slope all the way down. Don't give it away, Monica. Let the people think it out. Does it include that point? Does it not include that point? All right. Let's keep going. Number 2 is talking about non-differentiable, right? It is not differentiable at x equals 3. You need to figure out what type of non-differentiability is there, right? And there are 3 different types, right? Discontinuity, right, is one of them, right? It's not it's not differentiable there because it's continuous. But we know that this function is actually continuous. But if you don't know that, you can take a look at that function further. And there's also the other two, which is a cusp and a corner. And those are the other types. And why are those not differentiable? So give yourself a sentence to type for that. 3, 4, 5, and 6 are all just practice taking derivatives, right, with different functions and different rules. That's going to be that. This is the one I wanted to talk about, though. Number 7, and it was in the homework problems for some of you guys that you guys might have done, and some of you guys who haven't done it yet, you might not have seen this. So let's take a look at this problem real quick. I got 10 minutes. This is perfect. This is the one question I want to look at. And number 8 follows that same way in looking for a tangent line and whatnot. But we'll talk about this one right here. Write the equation of the tangent and the normal line. So some of you guys know what the tangent line is. Some of you guys don't know what the normal line is. And we'll talk about the normal line after we do the tangent line. Okay? So they want us to write an equation of a tangent line. This is the key word. They want you to write an equation of a line, pretty much. Right? In order for you to write an equation of a line, right? The equation of a line, do you guys remember it? There's two ways to write an equation of a line. One way is y minus y1 is equal to m times x minus x1. We call that point slope form. Right? And then the other way is y is equal to m times x plus b. And we call this one slope intercept form. Right? For calculus sake, writing an equation of a line is easiest using point slope form. You can use slope intercept form, but I don't suggest it. I don't suggest it. Point slope is going to be the easier one because all you need is a point and a slope. And most of the times you don't actually have the y-intercept, and it takes a little bit of effort and a little bit of work to find that. Okay, so here's the deal. We have a function right here, y is equal to x cubed minus 5x plus 2. And I'm looking for a line that's tangent to this when x is equal to 2. I'm sorry, x is equal to negative 2. Okay? So to calculate this, I need the slope. And in order for me to find the slope of my tangent line, that's just equal to the derivative. Right? That's just equal to the derivative, which is going to be equal to 3x squared minus 5. Right? 3x squared minus 5. But I want the tangent line at x equals to negative 2. Well, what does that mean? Well, that just tells me the slope of the tangent line at x equals to negative 2 is going to be equal to the derivative evaluated at negative 2, which is going to be equal to 3 times negative 2 squared minus 5. Right? Which tells me then the slope of the tangent line at x equals to negative 2 is going to equal to negative 2 squared is 4. 4 times 3 is 12. 12 minus 5 is 7. Did I do that right? Now, this slope right here is not your final answer because remember, what do they ask from you? They're asking for you the equation of a line, and all you've found is the slope of that line, and that's this guy right here. So, to write my equation of a tangent line, my equation of a tangent line, right? My equation of a tangent line is going to be y minus y1 equals to 7 times x minus x1. And here's the part that you need to realize. The x1 and the y1, right? The x1 and the y1, I'm going to move that down. Nope, I didn't want to do that. The x1 and the y1 are just the values of the points. x1 is a point, y1 is the y value of the same point. So what's x1 equal to? Well, x1 is the point right here, which is negative 2. So it's going to be negative 2 in there. What's my y1? You could figure that out. You know what the function is, right? You know what the function is. Plug in the x value, you'll get the y value out. So at x equals to negative 2, the y value of it is going to be negative 2 cubed minus 5 times negative 2 plus 2, which is going to give me negative 8 plus 10 plus 2. Right? So what's the y value of this guy? -8 plus 10 is 2 plus 2, y is equal to 4. All right, so the point that is in question is -2, comma 4, and I plug that into here. Y minus 4 equals to 7 times x minus a -2, and that right there is your answer for the equation of a tangent line. That's your answer for the equation of a tangent line. Before you go, what is a normal line then? What is a normal line? Do you guys know what a normal line is? Have you guys ever heard of that? If you are taking physics, you will learn of a normal line. You'll learn it as a normal force. And the normal force is just the line, just the force acting at a perpendicular line to the surface that you're dealing with. So if this is the tangent line, then you're going to have here the normal line. And for the normal line, it's perpendicular, right? That's all it is. Perpendicular. Now, for it to be perpendicular, do you guys know the relationship between the slope of a line and a line that's perpendicular to it? Do you guys know what happens when a slope is perpendicular to another slope? Any ideas? They're parallel? No, Dave, that's the opposite. That's parallel means they never cross. Perpendicular means that they form a 90-degree angle. And that's it, Juliet. They intersect, and of course, they are negative reciprocals. That's it. So if the slope of the tangent line was 7, the slope of the perpendicular line is going to be -1/7. Slope of the perpendicular line is going to be 1/7. And of course, it's going through the same point. It's going through the same point. So the slope right here is going to give me the new equation of a normal line, which is y minus the same point, which is 4. But the slope is the only thing that's different here. And it's going to become -1/7 x minus -2. And that's your equation of your normal line. That's your equation of your normal line. So taking a look so far, I've done number 7 for you. I've done half of number 1 for you. And there is a total of 14 problems on this review guide. You're already started on this thing, right? So get in there, get working on this. You have all of the weekend. Monday, we'll start talking about this stuff, and so on Tuesday as well. I'm not going to just throw you into this next test. I'm going to give you some time. We're going to do some problems, some extra practice problems in class on Tuesday to get you guys feeling comfortable with it. And then your test is next week on Thursday. Okay? Hopefully that helps you guys out. And that's it from me today, guys. The Desmos activity will remain open. So I really suggest you guys go in here and actually practice sketching what do you think the derivative would look like. And for example, what I would do here is I see that it's 0 right here, so I would draw a 0 right there. I see that it's 0 right here, I draw a 0 right there. The slope here is negative, and then positive, and then negative. So my slope would probably look something like this. God, I don't know how you guys do it with your mouse, but bam. That's what I think my derivative would look like. And you can go check, by the way, at the very end here. So this is the function. What does the derivative look like? It looks like that. How did it compare to my answer? Pretty darn close, I'd say. Pretty darn close. I'm just that good. I'm just that good. All right. When it asks to differentiate a function, is it just asking for you to find the derivative? Yes, Monica, that is it. That is it. All right. So if you have any questions on any of the review stuff, I will be in my office hours today. I'm sorry I couldn't be there in there yesterday, but I will be there today. And I will be there tomorrow from 1 to 2, right? And that's going to be it, guys. Have a good weekend. Stay out of trouble, stay out of jail, and don't get pregnant. All right? So long, guys. Farewell.